Okay. We are now live with our acid-base unit test review. And I typed in a bunch of questions, and Sierra has already typed in a question, which is excellent. So your questions as students take precedence over my stuff because I want to be able to address that. However, I do feel like if we can, we want to try to get to my stuff just because I tried to tailor it somewhat to the test. But I don't think that's going to be a problem. So I know you guys are still in the process of joining. So I'm going to give you guys a second to do that. And I'm going to start looking at Sierra stuff. And interestingly enough, we covered some of this last night in the Hangout that was not broadcast, which is fine. Okay. So you guys will probably join pretty quick. So I'm going to go ahead and select Sierra's question. She said, can you go over worksheet 14S, problems 1C, 2, and 3? Also, I'm getting really confused with Ka, Ka1, Ka2, and how to solve when given molarity. So there's a lot of questions all wrapped in one, and but I think we can do that. So let's go ahead and start from the top. Worksheet 14S. 1C. So we have this benzoic acid with a concentration of 0.10 molar, and the pKa for benzoic acid equals 4.2. Assume the degree of ionization of benzoic acid is negligible. So not too bad. And the original question is calculate the pH. So this actually relates to another question that I posted about relating pH, POH, H plus, OH minus, Ka, Kb, and Kw. And so we're gonna jump into that. So why don't I go ahead and share my Google, not my Google, my Bamboo tablet. There's another name for it. There it is. And I found myself needing to make a grid last night because of the way that I was writing. And I didn't do it last night, and I wish that I had. So hopefully this will be a little bit easier tonight. All right, so we're on worksheet 14S, and we're going to start with number 1C, and benzoic acid, concentration of 0.10. So we don't really care about the formula for benzoic acid, but what we can say is that when it talks about the degree of ionization of benzoic acid, it's probably talking about multiple H's. It's talking about other things that aren't going to come into play. Adrian Dingle teaches some organic chemistry, so that might be something that he's relating it to. What we are going to do is we're going to call benzoic acid, we're just going to call it B and Z. So the concentration of B and Z is equal to 0.10 molar, okay? And because we're doing that, we can just call it HA, because that's our generic term for acids. All right, and the pKa they gave us was equal to 4.2. Well, we do very little with pKa. The only time we've really used pKa is in the Henderson-Hasselbalch equation. This is not a buffer. So let's get it back to its Ka form. And if you remember that if you do the negative log of something, like the negative log of the H plus concentration is pH. So the negative log of Ka is the pKa. Well, to get it to go backwards, what you have to do is Ka is equal to 10 to the negative 4.2. So 10 to the negative of something will give you whatever the original is. So sort of like pH is equal to something like 1.0. Then the concentration of H plus is equal to 10 to the negative 1.0. Okay, so there's a little pattern here you can say. So in this case, Ka is equal to, and use your calculator. So 10 to the negative 4.2. Okay, so now we're going to write these on here, but I'm going to carry these in my calculator because really the final answer is a little bit ways away, so we're working our way towards that. So I'm just rounding it for now just to put it on paper. So 6.3096 about. And that's the Ka. Oh, it's times 10 to the negative fifth. I probably should have cut my number short a little bit. And I'm leaving it in my calculator so that I can have it to use for other things, okay? And we have Ka is equal to the concentration of the H plus times the concentration of the A minus all over the concentration of HA. And we just said that the HA is the benzoic acid. And if you remember, the H plus and A minus are both usually represented with an X, okay? So we already have two of our numbers. We have 6.3096 times 10 to the negative fifth for the Ka is equal to, and since when it dissociates evenly into H plus and A minus. We've talked about this in class. So that means that it's going to be X squared over the concentration of HA, which is 0.10 molar. Okay? So now we're going to have to isolate the X squared. So we multiply both sides by 0.10 molar times 0.10. Wow. This is not really helping me, is it? 10 and times 0.10. So let's see, take that same number times 0.1. And I don't even know why I use my calculator for this. I'm embarrassed. That's okay. 6.3. Oops. Oh no, what happened? There we go. 6.3096 times 10 to the negative 6, because of course it's 1/10, is equal to X squared. So now we need to take the square root of both sides. And then X is equal to, and we said up here, it's the H plus concentration. H plus is equal to, I'm going to do square root of that. Second function square root, second function answer. And I get 0.002511 molar, which is the same thing as you could say 2.511 times 10 to the negative third molar. Okay. Now, that's well and good, but we're not finished yet because it was actually looking for the pH. And if you remember from what I said at the beginning, pH is equal to the negative log of the H plus concentration, which means that pH is equal to negative log of 2.511 times 10 to the negative third. So I'm going to do negative log of our answer. Remember, I'm still carrying this in the calculator. I haven't rounded anything yet in the calculator. And so that means that according to my calculations, the pH should be equal to 2.6. And if I look at the key, that is exactly what it came out with. Let me see if I can to show you the key really quick. And there it is. Oh no, did I show the same thing again? No, there it is. 1C, 2.6. Yay! Okay, so that's the first one down. Let's go on to the second one. All right. So, well, let me come back. Actually, let me go back to the bamboo tablet really quick, because we're talking about the interrelation of these different things. So basically, what we've just covered is we've talked about how pKa and Ka are related, or pH and the H plus, okay? And right here, the Ka and the H plus, okay? So we have this right here. You could say that, if you want to rework that, you could say that the concentration of HA is equal, no, that's not what I wanted, I'm sorry. I'm writing this wrong. Let's try that again. The concept, and I actually introduced this to you guys at one point right before I did the Henderson-Hasselbalch. The concentration of H plus is equal to Ka times HA over A minus, which is kind of funny because then if you rework this, you get pH is equal to pKa plus log of base over acid. Okay, so you did the negative log of each of these, and that's what you ended up coming with. So it's a derivation, but you can see, I mean, maybe that sort of makes sense. Those of you that have a more math-related mind, it kind of connects. If you don't, ignore all of that and just focus on this equation. This is the key to doing a lot of different things. If you can find the H plus, and you know that it's going to be X for both of those, then you have Ka is equal to X squared over HA. Okay? Let me write that down here. This is a true statement. This will always be the same. Ka is equal to X squared over the concentration of HA. And so they'll often give you the Ka of a substance, and they'll often give you the concentration of its, like it's a weak acid, they'll give you the concentration of that weak acid, and then ask you to find the pH. So basically, the X is the same, the X is equal to the concentration of H plus, and once you have X, you can then do pH equals negative log of H plus, and that will give you the pH. So that's the sequence that you would go through on how to solve that. So hopefully that makes some sense. You will probably have to do that. I can't remember if I have that exact problem, but I definitely have some variations of that on my test. Okay, so let's go look at the number 2 for her question. There we go. I believe it was number 2, right? 1C, 2 and 3. Okay, 2. A buffer that is made of 0.10 molar propanoic acid with a pKa equal to 4.9 and 0.050 molar sodium propanoate, calculate the pH. So actually, I think number 2 is even a little bit easier than 1C, but of course I would say that. So this is now with a buffer, we're going to be using the Henderson-Hasselbalch equation. So let me skip on over to the next page and erase whatever that was that I made. Okay. All right, so I like blue. So we're doing number 2. All right, and again, you don't really have to know the formula for the propanoic acid, but when you look at it, if it's got propanoic acid and sodium propanoate, they're probably related, right? They're probably conjugates. And if you remember, conjugates are usually like us, especially now. I mean, the stuff that we're really going to calculate is a weak acid and its salt, or a weak base and its salt. And if it's the salt, if it's a weak acid and it's salt, then it's usually got some sort of a metal cation with it, okay? And if it's a weak base plus a salt, there's usually some halide anion. That's usually what it is. It's kind of a funny thing, okay? So in this particular problem, we have propanoic acid, which we're going to represent with, we're going to have HA, because I like that as a generic term. HA is equal to the concentration 0.10 molar, and the concentration of NaA, right, that's its salt, is equal to 0.050 molar. So this is the acid, and this, okay, so if it's a weak acid, that's its conjugate base of the salt. Weak base is a conjugate acid. So really, we're looking at this one right here. Okay, and so this is the conjugate base. Weak acid with the conjugate base. And our pKa is equal to 4.9. Now, if you remember the Henderson-Hasselbalch equation, that is pH equals pKa plus log of base, so the concentration of the base over the concentration of the acid, okay? Because when you have the Ka, the acid's on bottom. If we had POH equals pKb, then we would have acid over base. Again, we're looking for pH, and I think this makes it a little bit easier. pH, therefore, is equal to 4.9 plus log of the concentration of the base, which is 0.050 molarity, divided by the concentration of the acid, which is 0.10. All right, and according to my calculator, 0.05 divided by 0.1, I take the log of that, which is 0.5, which I probably could, oops, log of 0.5 is this quantity right here is equal to negative 0.30102999, etc., blah, blah, blah. So we have pH is equal to 4.9 plus that number, and we get 4.59897. Now, sig figs with logs, the log of the number, so however many decimal places there are after the number, however many decimal places there are after the decimal point, that's how many numbers are in your log, or in your pH. So there were 2 numbers here, there were 3 numbers here, I think you have to go 2. So the pH, when we round that, is equal to 4.6. So I believe that's the answer. Let's see what it says. For number 2, it said 4.5. Wonder what I did. 4.9 plus the log of the base over the acid. For number 2, right? Calculate. Did I not add that right? No, that's it. I wonder how he got 4.5. I mean, obviously, on my test, I'm not going to mark you down if you put 4.5 versus 4.6, but on the AP exam, you might lose a point. How did they get that? A buffer is made of 0.10 molar propanoic acid, pK 4.9, and 0.05 died. 0.05. I would disagree with his answer. I would say it's 4.6, but I didn't write this test, so well, it is good enough for my test right now. You guys are on the right track. And if it was an actual AP exam, you show all this work. If it was like a 3-point question or a 2-point question, you would get everything but the last point potentially, depending upon it depends on sig figs, depends on how they're rounding the answer. So let's just go with that for right now. All right, we're on to number 3. This is taking longer than I thought it was. That's okay, we can do this. Number 3, unfortunately. A 0.10 molar solution of weak acid has a pH of 2.8. Calculate Ka and pKa, assume the degree of ionization of the acid is negligible. All right. We can do this. Remember, this is the interrelation of the different substances of the pH and the H. Okay, let me go to my bamboo tablet. All right. Let's go ahead and go to the next page. Okay, so when you look at this, remember I said that most of the time they give you the Ka. So this is number 3. Most of the time they give you the Ka and the concentration of the molecular acid, the weak acid, and they don't, or I'm sorry, so they give you the HA, which in this case is 0.10 molar, but they didn't give you the Ka. So you're like, oh, we got gypped. However, if you remember, your Ka is equal to your H plus times your A minus over the HA. Oops, over the HA. So usually they give you these 2, but this time they didn't give you the Ka. They gave you the pH. So if you look at that, okay, so I have the HA. So what other pieces of information I have? Well, if I have the pH, I can get the H plus. Remember, So pH is equal to negative log of the H plus concentration, which means that the H plus concentration is equal to 10 to the negative pH. So my H plus concentration is equal to 10 to the negative 2.8. So I plug that in, 10 to the negative 2.8. And that means that my H plus concentration is equal to 0.0015848, et cetera, et cetera. We're going to call that 1.58 times 10 to the negative third molarity. And if you remember that the concentration of the H plus is basically equal to the concentration of the A minus. I keep referring to this. This is the HA, the weak acid is dissociating into H plus plus A minus. There's always the assumption that it is one hydrogen is coming off and that it's 1 mole to 1 mole. So they're equal. So H plus and A minus are the same, which means that Ka is equal to, when we talk about these being the same, and these are both X, it's X squared over the HA, which in this case means, and H plus is here, so this is also X is equal to that. That's 1.58 times 10 to the negative third squared divided by 0.10. So I'm going to square that number, answer squared, and then divide it by 0.1. For the Ka, my answer becomes 2.51 times 10 to the negative fifth, and pKa is equal to negative log of the Ka, which means that pKa is equal to negative log of 2.51 times 10 to the negative fifth. So negative log of that answer. And my pKa ends up being 4.6. So that's my pKa, that's my Ka. Let's see if I got these ones right, according to that key. All right, so for 3, Ka is 2.51 times 10 to the negative fifth, perfect, and pKa is 4.6, perfect. So that works for that one. Good. All right, the rest of your question was, also I'm getting really confused with Ka, Ka1, Ka2, and how to solve with when given molarities. So I would say that in the process, and I'm going to go back to the bamboo tablet. And going back to this, we've talked about, we've answered the question about how to find pH given molarity. You know, that's basically, they're always giving you molarity. They always give you the HA, it seems like. And the concentration of the H plus and A minus, they're both X, they're equal. So if you find for H plus, you've got, that's X squared. Or if you have to solve for H plus, you know, and pH is tied in there. And we've covered that one back and forth, I believe. So that one hopefully explains that. Your next question, though, about how do Ka, Ka1, and Ka2 relate? Well, Ka1 and Ka are the same thing. If I have, let's do an acid, let's do H2SO3. Or actually, you know what? I know what I'll do. H3PO4, that's a moderate acid. It's kind of a weak acid. So when you have H3PO4 dissociating a little bit into H plus plus H2PO4 minus, right? This is Ka1. This is the first H plus coming off. Ka1 is equal to H plus times H2PO4 minus all over H3PO4. That concentration. That's Ka1. That's the first H plus coming off. okay? Then you have H2PO4 minus in another one. And the Ka for this, Ka is equal to something like, let's just say 2 times 10 to the negative third, okay? H2PO4 minus dissociates into H plus HPO4 2 minus. And this is Ka2. So Ka2 is equal to the concentration of H plus coming off of this one times HPO4 2 minus all over H3. Oh, I'm sorry, not H3. Haha. H2PO4 minus. And this is Ka2, and it's usually somewhere in the neighborhood of, like, let's say 2 times 10 to the negative. Gosh, I don't even remember for sure, but let's pretend like it's 10 to the negative 8th, because it's quite a bit lower, okay? Now, there's another one, HPO4 2 minus dissociates into H plus PO4 3 minus. And this is Ka2 because the third H plus came off. So as you can probably guess, Ka3 is equal to H plus times PO4 3 minus all over HPO4 2 minus. And Ka3 starts to get ridiculous. It's like 2 times 10 to the negative 18th or something. It takes a huge jump. So Ka is usually just related to a monoprotic acid, like a single proton. So your oops, I did it again. So your Kas, if you have just a, let me do this. A Ka, you're going to be dealing with monoprotic, okay? So you've got C2H3O2, right? The acetic acid, the HCN, the cyanic acid, okay? When you have Ka1 and Ka2, etc., it's di and triprotic acids, okay? Hopefully that makes some sense. So you would see that on some problems, and it might come up on the AP exam. I don't remember if I have it on my exam. All right, so that answers, that would answer serious questions, I believe. I hope that answered your questions. Okay, so let's go on to the next one. The next one I see is ARIAs. Could you do number 6 on the acids and bases practice test? Absolutely. All right. Did I open that one up? Acids and bases practice test. Number 6. Okay. Okay. I think I have this one. Yeah. Okay. I believe this is one I gave you guys. And your question that you're asking is about when solid potassium oxide is dissolved in water, which of the following is the strongest base in the resulting solution? Think about net ionic equations. Okay. We can do that. Let's make that formula. Now, this is part of, you guys are having to incorporate your knowledge from first semester in here. Okay, when solid potassium oxide. So potassium, oops. So this is number 6 on the practice test. Okay. Potassium oxide is K plus and O2 minus. So when you do swap and drop, you get K2O. And it's dissolved in water plus H2O. This has an alkali metal on it, so it is soluble entirely soluble. So when you end up doing that, you end up with some K pluses, 2 to be exact, floating around, plus your O2 minuses, and then your H2O. And the H2O, it can dissociate or whatever. And it said, okay, which of the following is the strongest base in the resulting solution? Now, when it separates out like that, you end up, because the H2O it's an H plus, plus an OH minus, right? Because it's not pure water. It's not, if that makes sense, not entirely pure water. What ends up happening, I guess what I'm trying to tell you is when you get around to this, what ends up happening is that you end up making KOH, okay? Whenever you have these metal oxides, it's one of the, it's a reaction type. So metal oxides plus water give you a base, okay? If you do a non-metal oxides plus water, you're going to get an acid. So K2O plus H2O gives you KOH. Okay, and because it's soluble, the K ends up coming off. You get this K plus OH minus. So KOH itself isn't the base; it's the OH minus that's the base. So that's an example of that. Non-metal oxide would be an example like. Why am I having a hard time with this? Oh, like NO2 plus H2O, and you end up with, you could end up with HNO3, which is the nitric acid. So, and of course, it's really just, you get a lot of H plus and NO3 minuses, which is similar in that same way. But I don't think I have a question like this. I think I have the test right here. You need to know what happens when you have hydrolysis, but I don't believe I have one of those particular questions. They don't have very many of those types of questions anymore. Like, you don't have to memorize this. So I wouldn't spend a lot of time, I would not spend a lot of time, like this right here, I would not spend a lot of time trying to memorize that or remember that. It won't pop up very frequently on tests, so. Okay, well, good. So, but that is standard. That's something that they expected everyone to know a long time ago. Not a long time ago, a couple of years ago. All right, so the next one I saw was Connors. He's got 17, 18, 19, or 20 on lecture 31 about setting up net equations with acids and bases. Okay, so the downside is I don't think I have that open on my computer right now, but it could, I could have it in my hand. Not in my hand, I mean sitting next to the computer. All right. Oh, good. Oh, yes. Okay. I like these. I like these a lot. This will be good. Be good. All right. So this would be, oh, I don't like the blue though. I mean the red. I want the blue. Let's try this. So lecture 31 and 17 through 20. Okay, so number 17. And this is the ironically, this is hydrolysis. This is kind of one of the questions we talked about. So you've got ammonium nitrate, NH4, ammonium. Ammonia is NH3. Ammonium, the extra M is an extra H. NH4 plus, and it's nitrate, NO3 minus. So really that formula is NH4, NO3. So that's a salt, right? This right here is the conjugate acid to NH3, which is the weak base. Okay? So you've got NH4NO3 plus H2O, right? So let me write that out in a more legible manner, or at least what I hope will be a legible manner. NO3 plus H2O. Now nitrates, I'll make that orange. Nitrates make most things soluble. Nitrates, you have to memorize this. Nitrates make things soluble, as well as alkali metals and ammonium. That is something you have to have memorized for the test. Okay? Which means that when it pops out the other side, the NH4 is trying to give up that, it wants to convert to the weak form, right? It wants to convert to this form. So you get NH3, and it hydrolyzes the water, and you get some OH minus, okay? And you probably, there's some, well, the NH, what does it do? Because NH3 plus H2O ends up giving you NH4 plus OH minus. Oh, that's right. No. I'm getting this wrong. Sorry. Plus, so that it gives up an H, making it NH, it gives you H3O plus. I'm sorry. I'm just getting them backwards. Okay. So what that means is this is, if you remember, this is the conjugate acid, and this is the weak base. But what it ends up doing is when you have that conjugate, that salt, okay, when it hydrolyzes with water, it becomes acidic. So if you have NH4NO3 or NH4Cl or something along those lines, the pH is acidic. Okay, because it produces H3O plus. Like the H came off of the NH3. The NH3 just wanted to be NH3. The H came off, right? So that you had an extra H here. The H came off and got added to the water to make H3O plus, which makes it acidic. Okay, so that's what's happening with that. Ammonium nitrate is the conjugate acid. You got that, it's going to be acidic. All right, so let's look at number 18. And I'm sure I'll do like 2 of these and you'll start to clue in on them. Potassium fluoride, KF, all right, plus water. So when you look at this, the K and the F, this was all about the conjugates question I had typed up there. KF are one of those, the conjugate of a weak acid or a weak base. Okay, up here, the NO3 was the conjugate of nitric acid. And so it doesn't contribute at all to pH. Down on this side, you have, you know what? I realized I didn't finish that off. Let me come back in a second. The F, however, is the conjugate to HF. So K, we could say, is the conjugate of KOH, which is a strong base. So that's not contributing to pH. The F is the conjugate to HF, which is a weak acid, right? And so that's our winner right there. So when we combine them together, we end up getting HF plus OH minus. So anything KF, NaF, what am I trying to say? LIF. I mean, all of those. So the pH is going to be basic. All right, so I want to talk about the hydrolysis. Now, on the next page, I'm actually going to write the net ionic equation, right? So number 17, we had, if you remember, we had the NH4NO3. A nitrate makes it soluble. So really, that's NH4 plus NO3 minus plus H2O yields NH3 plus H3O plus NO3 minus. So these NO3 minuses go away, leaving us with, as a net ionic equation, I'm going to make this in green because this will be the final answer. NH4 plus H2O yields, I can't write my things, NH3 plus H3O plus. And then for number 18, we had KF, alkali metals totally soluble. So you get K plus F minus plus H2O gives you K plus HF plus OH minus. The K's go away. Your final answer in green is F minus plus H2O yields HF plus OH minus. Okay. So I'm almost sure you're getting the pattern here. Let's look at 19 or 20. Which one looks better? Sodium oxide and water. Oh, that's pretty funny because we just did that one. That actually, we can skip that one then because that's very similar to number 6. When you have potassium oxide and sodium oxide, they're going to do the exact same thing. So just refer back to number 6 from the practice test. And so we'll not do that one. We'll do number 20, which is solid sodium acetate. So you've got Na, oh look, a totally soluble alkali metal, C2H3O2, one of my favorites as far as weak acids, and plus distilled water. So you have Na plus C2H3O2 minus plus H2O. Now this is the salt. This is the conjugate base to a weak acid. Okay. So when we do this, we end up with Na plus HC2H3O2, and we're left with OH minus because it stripped the H off of there to make the acetic acid molecule. And it's a molecule, so it's not contributing to pH as the molecule form. So the Na pluses go away. So your net ionic equation, C2H3O2 minus plus H2O yields HC2H3O2 plus OH minus. So the conjugate base to a salt is going to be, it's going to create a basic environment. It's going to, when it hydrolyzes the water, you're going to end up getting an OH minus. So hopefully that makes sense to you. That was all of those questions. Good. All right, let's do another one. You guys are doing good. I like all your questions. The next one I see on here is Mary Flake. Can you please review free response number 1C on the unit practice test? It would be my pleasure. All right, so I think this is it. Free response 1C. Okay. So we have, in this problem, methylamine, which is the CH3NH2 plus water. Interestingly enough, here we have a situation where it's hydrolyzing in water and it's producing, it's a weak base, and here's its conjugate acid, but it's producing a basic solution. They give you the Kb, which is very cool. They give you the salt, methyl ammonium nitrate. So if they put the NO3 at the end of this, that would be, oh, here it is. You can see that. And then in A, you determine the hydroxide concentration, 1.06 times 10 to the negative 2. Oh, I don't seem to have the answers on this. That's a shame. Well, I guess that's why we're doing this. So what percentage of methylamine molecules are associated in A? And that is just, you do the OH minus divided by the total concentration, which was 0.225 times 100. That gives you that. What is the ratio of this? So this is a buffer. So this is kind of fun. And this totally relates to what I want to do. This is good. You guys are asking all the questions I wanted to cover. So this is wonderful. All right. So now I'm going to write this up on the paper. And we have, this is free response 1C. The ratio of the concentration of methylamine to methyl ammonium nitrate. So we're looking for methylamine, CH3NH2, the ratio to the nitrate, which was CH3NH3 NO3, because of course this was a plus and this was a minus. And they give us the pH. How nice. pH is equal to 9.5. And so if it's a buffer and they give you the pH, you're probably dealing with the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the base, the concentration of the base over the concentration of the acid. And as it turns out, this is what we're looking for right here, this number. It's this number right here, okay? This is the base, and this is the acid, right? Conjugate acid, weak base, conjugate acid, okay? Now, in order to do this, we're gonna need some new information that hasn't already been given to us. They did give us the Kb, okay? And I want to talk about this, the relation of, so Kw is equal to Ka times Kb. So to manipulate this, and we want to know the Ka is equal to Kw divided by Kb, which is equal to 1 times 10 to the negative 14th divided by 5.25 times 10 to the negative 4th. So I plug that into my calculator. 1 second function exponent. Negative 14 divided by 5.25 second function exponent. Is that right? Negative 4. And the Ka is equal to 1.9048 times 10 to the negative 11th. Okay. So, so again, pKa is equal to negative log of the Ka. So pKa is equal to negative log of 1.9048 times 10 to the negative 11th. pKa is equal to negative log second function, because I'm still leaving this in my calculator. It's so much easier to do it this way. So the pKa is equal to 10.72. And again, I'm kind of keeping in the calculator. There's some rounding that might need to happen, but it'll be fine. So if we go back to this equation right here, we have this right here. pH 9.5 is equal to the pKa 10.72 plus log of, and the ratio basically is just x. Whatever that ratio, base to acid, that's just x, okay? So now we're going to subtract 10 to the negative, we're going to subtract 10.72 from both sides, not divided by, minus 10.72. So, okay. So log of x is equal to negative 1.22, all right? And we know that x, we do that, if you remember that, so pH is equal to negative log of the concentration of H plus. So if we reverse that around, H plus is equal to 10 to the negative pH. So that negative carried across. Well, over here, the negative is already over there. It would be like if we could make it, right? We could divide both sides by negative 1, and we could make that negative log of x. So since it's already here, you are not canceling it out, I guess is what I'm trying to say. 10 to the negative of 1.22. I believe that's right. Second function, 10 to the x. Sorry. And wait, what am I looking for? I gotta forget. Oh, the ratio of the base to the acid. Did I do this right? Oh, I'm sorry. Hold on. Just give me 1 second. This will take me but a moment. I am forgetting right offhand. I am forgetting right offhand about that ratio, or I'm not the ratio, the 10 to the negative. If it's already negative, I think you can just, oops. I think if it's already negative, you just do it. So I think the ratio is 0.06, but I want to just confirm that. And I thought I had the key. I think I don't know if I put it on your guys' key. And this is what would be really helpful. If you guys were in the Hangout with me, you could tell me. I don't know if because I think I got this one off of this key. I got off my computer, not the one I had at school. So I don't know if I filled it out in the. I don't know if I put it in the. For you guys, I guess is what I'm trying to say. Are you guys following that? Yes or no? See, I can't ask you guys right away. Just give me a second then to look up and see if, because I want to confirm if I did that right before we continue. I want to make sure I give you guys the right answer. This is the acetic acid one, right? I'm having a hard time finding this in my. Actually, I'm having a really hard time finding this. Well, I believe that's it. Okay, so here's the deal. This is what I'm trying to figure out. So if I had, remember this, okay, so the pH is equal to negative log of the H plus concentration. So negative log. So here, there's no negative here, but if I divided both sides by -1, then this would become negative. And I would have negative log of X is equal to 1.22. So it should be X is equal to 10 to the negative 1.22, which is what I did. And so the ratio of base to acid is actually a smaller, it doesn't work out really well. Usually they do it, usually it's done in a whole number ratio, but the ratio would give you 0.06 as your ratio of base to acid. So, which is a little unusual. If you were to flip it around, you'd probably get a different, as far as acid to base, you get a different number. But that should be the answer to 1C. So I am sorry if that I was having a hard time finding the key just to confirm the answer. But this is the answer, 0.06. So that wraps up number 1C. Okay, now I thought I had seen a question from Angela Hung. Oh, how do you figure out which solution has a higher, lower pH in relation to other solutions? Which solution has a higher or lower pH in relation to other solutions? That is a great question. I am not sure which one you're referring to. Well, I'm not sure what your question is exactly. Okay, so if we have a solution of that's clearly an acid versus clearly a base, right? You know which one's higher or lower. If you have I wish I knew which question, if there was a question you're referring to. Is it a buffer? Is it, maybe it's a buffer. If I look at the practice test and we go up here and we compare these, NH3 and NH4Cl, you have a weak base plus its conjugate acid. Well, that's going to be a basic pH. Here you have a weak acid and its conjugate base, which is going to be an acidic pH. So that's a low pH, and this is a higher pH. HCl and NaCl. NaCl is completely a salt. HCl is acidic. This is probably going to have the, of these three, it's going to have the lowest pH because while this is a buffer, this is still a weak acid. If all concentrations are 1 molar, more HCl is going to dissociate than H3PO4, which means its overall pH is going to be lower. And then we look at NOH and NH3. You have a strong base and a weak base. Well, they're both basic. That's definitely going to give it a lot of basic pH, and this is going to give a little bit more. So this is going to give you probably the highest pH. And then finally, you have a weak base and a weak acid, which if they're 1 molar, and it just so happens that, it really depends on their Ka and Kb. It just so happens that both of those have about a 1.8 times 10 to the negative fifth. It's kind of coincidental, but it works out really well for a lot of examples. Since their Ka is equal to the Kb, it's going to be pretty much neutral. It's going to be the most neutral solution. So the NH3, C2, H3O2. So if we start from the lowest to the highest, the lowest would be the HCl, NaCl. Next would be the H3PO4, NaH2PO4. So you have an acid plus a salt. A strong acid plus a salt is going to be the most acidic. A weak acid plus its conjugate salt is going to be the next lowest. The NH3, the ammonia and the acetic acid, the weak base, weak acid is going to be neutral. So that's going to be the next one as you're moving up. Then it is the weak base plus its conjugate acid. That's going to be a buffer. It's going to be a little bit higher than neutral, whereas the B is a little bit lower than neutral. So this is a little bit higher. And then a base plus a weak, strong base plus a weak base is definitely going to make it very basic. So that's going to be the highest pH. So if I'm assuming that you're talking about a solution when you're combining two things, that's my best guess based on what you said, because otherwise you're comparing strong acids or strong bases, or I mean, it's kind of obvious. The only other way when you're comparing them is knowing their respective Kas, and the higher the Ka, the stronger the acid, or the higher the Kb, the stronger the base. The lower the Ka, the weaker the acid. The lower the Kb, the weaker the base, and the weaker they are, the closer they are to neutral. So that's my best guess on what you were asking. Hopefully that answered that question. But that's a good thing to know. Or at least I don't know if that was your actual question or if I just tailored that into what I thought you needed to know for the test. Hopefully it was helpful. Okay. So are there other questions from you guys? Yes, Aria, multiple choice number 14. Okay, let's take a look at that one. Multiple choice number 14. We've got, oxalic acid is a diprotic acid with Ka1 and Ka2. Wow. Which of the following is equal to the equilibrium constant for the reactant represented above? Okay. So, excuse me. I'm going to show this on my paper. And this is one of the properties of the Ks you need to be familiar with. So K total is equal to Ka1 times Ka2 times Ka3 ... Okay? Your equation is H2C2O4. This is a diprotic weak acid, which is why we have the Ks, right? Plus 2 H2Os, we know where this is headed, 2 H3O pluses plus C2O4, 2 minus. So we stripped both C's off that, okay? The 2 H2Os, 2 H3Os, so 2 H3O pluses. Now, if, we'll go to green. If Ka1 is equal to 5 times 10 to the negative 2, and Ka2 is equal to 5 times 10 to the negative 5, and they were both done at the same time, which is very unusual, but let's say that it came in, you had a strong base, just ripped them both off. You're gonna have a K total, which is what they're looking for, is equal to Ka1 times Ka2. So, and you can do this without a calculator because it's the multiple choice you have to. K total is equal to, let me get down here, there's more space. K total is equal to 5 times 10 to the negative 2 times 5 times 10 to the negative 5th. And so what happens is these 5s come out and you get 25, and these get added together times 10, so because you add exponents, 10 to the negative 7th, and that's not the correct scientific notation. You can't have 2 digits, so it's 2, you take a 10 out, so it's 2.5 times 10 to the negative 6th. Oops. And so that's your answer to number 14, or that's how you calculate it. Okay, done. All right, looking at other questions. I don't see other questions. So I'm gonna quick run through the questions that I put up, and hopefully these work. So the first one is, what is a buffer? What makes it up? How does it work? And how do you find pH? So that was on the Q&A that I put that you needed to know. So a buffer is weak plus salt. So that could be a weak acid plus its salt, which conjugate base, or a weak base plus its salt, which is oftentimes a conjugate acid. And if you're doing this, remember that the weak acid, it's usually is, you have, to give you guys examples, plus salt, it's usually the HA plus NaA, right? So HC2H3O2 plus NaC2H3O2. And if it is a weak base plus its salt, it's oftentimes NH3 plus NH4 plus, and then like Cl minus. So actually it would be written like NH3 plus NH4Cl. Or if it's organic, you have a CH2, is that right? Let's do it, CH3 NH2 plus CH3 NH3Cl, something like that, okay? And so they resist strong changes in pH. That's how they work. They resist strong changes. So you can add strong acids or strong bases to it, and it won't fluctuate in pH greatly, which is kind of nice. And the way that you would find pH for that is the Henderson-Hasselbalch equation, PHH equation. pH is equal to pKa plus log of the base over the acid, okay? And of course, its corollary is pOH is equal to pKb plus log of the acid over the base, okay? We don't use that one very often. It's usually looking for pH, and so we usually use, gotta be honest, I mean, it's probably just easier if you just don't even worry about the other one, just this. And you just have to know how to manipulate between pKa and pKb and pH and pOH. Work that out. So that's how you would solve for that. Okay, done on that one. All right. What is titration? How do you do calculations? So a titration is a reaction between acid and base. The formula for that is the molarity of the acid and the volume of the acid equals the that's when you get to, this is neutralization. Titration is, the purpose of a titration is like a neutralization. You want to see it finds concentration of unknown solution. Unknown solution. Okay, so oftentimes you know how much you have of this unknown acid or unknown base in a flask, but you don't know what its concentration is. And so that's where, you know, that's your analyte. So if we have here a burette. Okay, so this, and okay. And then you have, let's say, we'll just use a beaker. And so what's in here? Oh, I made that line way too high. Okay, let's try that again. So this is your analyte, because this is what you're trying to analyze. And this, we could make it like, let's make it, well, I was gonna make them different colors. Let's say that you're, actually, that's really good. Actually, let's leave the blue. So this is, we're gonna say, and this is your titrant. And so maybe this is your base, and they're just like our lab. And your analyte, we're gonna call that your acid. It's in here, okay? And so you are using that to determine, so that you usually know, this is known up here. Known concentration. And then you also know the volume that you have titrated. And so then once it goes in, you can see, you know the volume of your analyte, and then you can find the concentration, the molarity. So maybe you're looking for the molarity of your acid as an example, okay? So let me just think for a second. If you were, okay. So when you do this, this works really well for the, if both, because really what this boils down to, MAVA equals MBVB. This is one of the harder parts of this equation, is that this is the moles of H plus being at the equivalence point. At the equivalence point, the moles of H plus is equal to the moles of OH minus. That's really what this equation is about. Unfortunately, what happens if you have a diprotic acid or you have a base with more than one OH minus? Okay, so if that happens, MAVA equals MBVB. If you have H2SO4 for your acid, then you're going to have to double molarity, because both those H's are going to come off. So it's really 2 times MaVa. If you have H2SO4 plus NaOH is equal to MbVb, okay? But let's say you had HCl plus calcium hydroxide. I think that's a strong base. Yeah, CaOH2. So then you have MaVa equals, where did I buy it? It's equal to 2 times MbVb, okay? And so here's the interesting thing. Let's say if you know the concentration of the base, then you just multiply it by 2. But let's say you don't know the concentration of the base. That's your analyte. That's the one that you're looking at. What you're going to end up doing is you're going to end up dividing both sides by 2. Your Mb is equal to, we should do it like this. Your molarity of your base is going to be equal to the molarity of the acid times the volume of the acid divided by 2 times the volume of the base. You know, if you know what the substance is, but you just don't know what its concentration is. So you're gonna have to, you know, pay attention to what's going on there. Make sure you're using the titration equation calculations correctly. Yeah, yes, and that's correct. Okay, now, so that answered that question. How to determine strengths of acids and bases by looking at them. And that's kind of what I funneled the Angela's question into. But the next thing I was going to look at is when you start looking at them, things to compare. Like, which one's the stronger acid? If we have HClO4, HClO3, HClO2, HClO. Which one's stronger? Well, this one, because it's the more oxidized. The more oxidized the acid is, the stronger it is, okay? And we talked about that a little bit, the H plus, and you have Cl, and you have these oxygens coming off, right? Oxygen, 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 oxygen. And these oxygens are all pulling, like it's let me make it a different color. The electronegativity, because oxygen is more electronegative than chlorine, not by much though, but it is, it's pulling this way, which means it's pulling more this way, which means it's easier for the H plus to pop off, which is why the fewer oxygens are on the outside, the more strongly that oxygen can hold on to that H on the outside, okay? Now, but that's different than if we had HOCl, HOBr, HOI, and HOF, okay? Which is interesting because it's the corollary to this a little bit, HF, HBr, HI, HCl, okay? So these are all strong right down here. I probably should have written them differently. Actually, it'll make more sense. I was doing it randomly on the left, but on the right, I'm gonna make it more in line. HF, HCl, HBr, and HI. So as they go down, so HI is greater than HBr, is greater than HCl, which is greater than HF. Because as the size of those ions, the size of those atoms get bigger, like it won't be able to pull the H's as tightly, okay? So the H comes off more easily off the HI, making it a stronger acid than HBr and HCl. And HF, it's a much more electronegative element, right? I is a less electronegative element. F is a more electronegative element, so it's going to hold on to that H tighter, which makes it a weaker acid because the H doesn't come off. So at the same time, when we look at these ones, wait, did I have this on the sample? Actually, So it kind of relates to number 5. I thought I had, I'm looking at the practice exam. Well, it's kind of similar to that one because you have an H bonded to an O bonded to an F, right? It's more electronegative. It pulls it tighter going this way. Versus the HOI, which does not. It's less electronegative. So it's actually pulling more this way. The oxygen is more electronegative than the I. So because it's pulling this way, it cannot pull on the HF as greatly. So HOF, it becomes a stronger acid than HOI. Because here, the oxygen holds on to its electrons and it pulls both sides, okay? But here, its electrons, its electronegativity, I should use red for this, it makes it a lot easier. The fluorine's pulling it more this way, so that means there's not as much pull going this way or pulling on the H. So the H pops off easier there, whereas in the HOI, the I is less electronegative. It's so much larger. It can't pull on the oxygen very strongly. The oxygen ends up pulling a lot more on the I, so it ends up pulling on the H a lot more strongly as well. So hopefully that makes sense. All right, we better pick this up. It's 10:16. Oh my goodness, this was long. The question of pH, POH, H plus, OH minus, Ka, Kb, Kb. I talked about all that already, so I'm going to assume we're fine. If you saw this question, gosh, I don't know which question to go back to, but it's you know what I could do is I could flip back page-wise. And we've talked about it throughout. Here on page 8, the Kw equals Ka times Kb. So this was free response 1C. So there's some talk about it there, pH and P and relating to H plus. So that's mostly what I want to talk about there. Okay. The next question, what are conjugates? Are they stronger, weaker? How do you find pH? We've been working on that throughout the entire program. That's been almost a part of every question. So I'm not going to go back and talk about that one. And finally, I did want to talk about this sort of a definitions side. So let's just talk about this briefly. And then if you guys have any other questions, you should type them in now, because once we get done with this one, unless there's another question that will end. So Arrhenius, blue, I want to go with blue. All right, so Arrhenius, it means it's an H plus donor. Oh, I'm sorry. No, that's not right. It increases the H plus concentration if it's an acid, and if it's a base, then it increases the OH minus concentration. But not a very popular definition in. It's not a very popular definition in AP Chem. They much prefer the Bronsted-Lowry definitions, where an acid is an H plus donor, and a base is an H plus acceptor. Okay, they love that, right? An example of a Bronsted-Lowry H plus donor. Most of the time, this is you combine them in the same reaction, but if you have HC2H3O2 plus H2O, you get C2H3O2 minus plus H3O plus. So here, this is the Bronsted-Lowry acid because it donated, and this becomes the Bronsted-Lowry base because the H got donated to the H2O, H3O plus. Okay. So water, both Bronsted-Lowry acid and base. So it's interesting. You can look at these. What are some examples of Bronsted-Lowry acids and bases? And usually it's acids that they usually refer to acids that are weak acids that are di or triprotic. So examples of that would be if we had H3PO4 and we said, oh, we're going to make it NaH2PO4, okay? So it can give up an H, so it could be Na2HPO4, okay? Or it can go to H3PO4. So it can do an acid or base. So when you see the NaHCO3, which is a form of the H2CO3, if they have, oh, I'm forgetting some of them right now. Why am I forgetting these? Well, it doesn't help very much if I don't have other examples. I think you guys get the general trend, though. So those are Brussels-Lowry acids and Brussels-Lowry bases. Now, what's it called when that happens? We call these amphiprotic. Amphiprotic is the same as being a Brussels-Lowry acid and a Brussels-Lowry base. That's what amphiprotic means. And the final definition I want to mention, of course, is amphoteric, which just means behaves. Wow, that's a horrible B. Behaves as acid or base. So in this situation, back here, these are also amphoteric because they're behaving acids and behaving as acids and behaving as bases. So quite frequently, amphiprotic and amphoteric mean the same thing. There are some examples where it's amphoteric but not amphiprotic. But of course, at this very moment, I can't think of them. They don't pop up very often, but you're going to see those terms used. And I just want you guys to be familiar with them so you're not confused. All right. So that is all the questions that I wanted to cover and that I think it was important to cover. And I got all your questions, I believe. I'll be there early tomorrow morning. If you guys have any more questions, please feel free to come in and ask. Make sure you get a good night's rest, though. That's more important than anything. And I'm sorry that this didn't happen last night. I don't know what I did to mess this up, but I'll have to figure something else out in the future. All right, guys. Good night, and see you tomorrow. Bye.